Okay. So before we had this break, there's a question to see an example of like something with an odd number in a cycle, an odd number of symbols. So like, let me just try and describe it with a picture to see, so we can kind of visually see what's happening. Here's a cycle. Here's one of the cycles. Okay, and each arrow represents kind of applying sigma once. So when we do it twice, we follow two arrows instead of just one, right? So this dotted line is like sigma squared. Right? And so you see by following the dotted lines, this 4 cycle gets split up into 2. There's 2 and 5. And 4 and 10. Okay, and so you can think about what happens with like say a 5 cycle. Well, let's just do the 5 cycle, 1, 2, 3, 4, 5. Okay, that is 1, 2, 3, 4, 5. And now I guess this is a good question. So what's going to happen if I do the same thing? Yeah, what's going to happen to this cycle if I follow 2 arrows? That is a question for you guys. Yeah, so I go from 1 to 3, and then I go from 3 to 5, and then from 5 goes to 2. At this point, with the 4 cycle, I had gone back to 1, so I had kind of stopped. But this, we just keep going, you know. And then from 2, I go 2 arrows to 4, and from 4, I go back to 1. Okay, so I still have a 5 cycle. So if this is sigma, then sigma squared is still a 5 cycle. It's the 5 cycle 1, 3, 5, 2, 4. Yeah, I mean, we get a star. I mean, if we get sigma cubed, when we do sigma cubed, we go by 3. We actually do, it's like sigma squared backwards. You go 1, 4, 2, 5, 3. Sigma to the 4th. Well, when we go 4 arrows ahead, it's like going 1 arrow back. So sigma to the 4th ends up being like 1, 5, 4, 3, 2. Well, maybe it's better to write it as 5, 4, 3, 2, 1. Okay. And then only when we do sigma to the 5th, when we travel by 5 arrows, that's like traveling by no arrows. So sigma to the 5th is always 1. Okay. So you saw when we have a 5 cycle, the different powers of sigma are still 5 cycles. That doesn't always happen, but it happens here. Okay. Okay. So I hope that example kind of gives you an idea of the different things that can happen. Okay. Um, so there is another important way that we can decompose cycles. Okay. So we have this definition. A transposition is just another name for a two cycle. And why do we give a two cycle a special name? Well, a transposition is like two symbols and you just switch them. So you just transpose two symbols. I guess that's why you call it a transposition. Okay. And there's a good reason to give a two cycle a special name. And that is because we can write any permutation as the product of two cycles. Okay, so we have a theorem. So let sigma be in Sn. Then there are transpositions. We'll call them T, T1, T2, all the way up to Ts, such that sigma is a product T1, T2, up to Ts. Okay. Now, these transpositions are not disjoint and they're not uniquely defined, but what we can say is, furthermore, whether S is odd or even doesn't depend, it does not depend on my choice of transpositions. I'll just say it only depends on sigma. Okay, so the number of transpositions I use, that number, it's like, that number, you can use a different number, but whether that number is odd or even only depends on sigma. Okay, so let's see what we mean. A trivial example, right? The identity, we can write the identity as a product of two transpositions, or we can write it as a product of four transpositions. Or I think we can write it more in a more complicated way. No, I don't want to write it in a more complicated way. Okay, just a moment. Okay, sorry again for the interruption. Okay, so you can see like the identity permutation, we can write it as, well, here, this can be the product of 0 transpositions, but it is also the product of 2 transpositions or 4 transpositions, or any even number of transpositions. Okay. What's another example? Here's a 3 cycle. Let's see if we can write that as a product of transpositions. Well, I mean, writing permutation as a product of transpositions is kind of like a game. Okay. You start from, so 1, 3, 2, that is really the permutation that looks like this. 1 goes to 3, 2 goes to 1, and 3 goes to 2. Okay, so the game is the following. You start from 1, 2, 3, and by switching only 2 symbols at a time, you have to end up with 3, 1, 2. So like, let's try switching 2 and 1. Okay, actually that was probably a bad move, but anyways, no, it's fine. Okay, and now to get to 3, 1, 2 from 2, 1, 3, we have to switch 3 and 2. So we switched switch 1, 2, and then we switched 2 and 3. And that's it, we did 2 switches. Okay. And now that is telling us that we can decompose this as the product of transpositions like this, right? Now let's try and let's just check that when we multiply these 2 transpositions, we get 1, 3, 2. So first we do 1 goes to 2, 2 goes to 3. So 1 gets sent to 3. Then we go 2 gets sent to 1, and 1 is left alone. So 2 gets sent to 1. And what about 3? 3 gets left alone, and then 3 goes to 2. Okay. Okay, so it's the product of 2 transpositions. But you can see there's more than one way to like play this game. There's more than one solution to this game. So there's more than one way to write 1, 3, 2 as the product of transpositions. I guess we could also write it as we could have, no, we could have yeah, we could have 1, 3, and then I guess 2, 1. Does that work? So 1 gets into 3, check. 3 goes to 1, 1 to 2. So that's good. And then 1 gets sent to 3. That's good. And 2 gets sent to 1, right? So this is another way to write the same 3 cycle as a product of transpositions. Okay. And the important point is that I used an even number. Okay. Okay. So just as a note, let sigma be an R cycle. And sigma can be written as the product of R minus 1 transpositions. Okay. And now actually I've gone on too long now. So just next time we'll see that we'll just introduce the notation of like permutations can be even or odd depending on whether you use an odd or an even number of transpositions to write them. Okay, so we'll try and do a few examples. And that will be it for today. Thank you for coming. Sorry for all the interruptions. Okay, yep. Have a good day, everyone.